You can see that these notes are pretty basic from the fact that, one, you only have one page, and two, we only have one objective, okay? Today is all about the scientific method. I know we did a sort of refresher on it at the very, very beginning of the school year, but now we're going to get a little more in depth. So hopefully by the end of class, you'll be able to list the steps, but also describe what that process really looks like. We're going to start with a little activity today, okay? I have a candle up here on my desk, and what I want you to come do is make some observations. You can jot them down on a scrap paper or at the top of your notes, and then I will light it, and you can make a few more observations, and then we'll come back and discuss. So to start off with, what kind of information do we write down?
Definite shape.
Okay. Shape.
Colors are dark blue and white.
Solid. Colors. What else did we write down? Height. Good. These are all really good things. Okay. Oh, you guys talked about melting point, that it melted quickly.
Low melting point.
If we had the right tools, you might even have been able to measure the temperature at which it melted. We didn't have those tools here today, but it would have been possible to gather that data. In the past, I've had students who have weighed the candle to try and get its mass, so that they could write that down. Okay, these are all examples of types of data that you might gather during a observation or during a scientific experiment. So the first step in the scientific method is observation. We've got to do some kind of observing. And usually people think that this step comes during testing, but really, if you aren't observing the world around you, you're not ever going to come up with any questions about how things work. So this step really belongs at the very beginning. Okay? You're going to start by taking measurements and collecting some data. What information do we already have? Okay? This data can fit into two categories. It can be qualitative, okay? This is descriptive data. Qualitative data is things like color, texture, okay? Or it can be quantitative data. This is numerical, things like height, melting temperature, okay? Anything with a number associated with it is going to fit in the quantitative category. Okay? And then, after we have gathered a lot of data about our situation, we are going to define our system. This is the specific region or area or location that you are going to test. So, for example, if you were testing the boiling point of water, your system would be the beaker with the water in it. Okay, if you were going to test something like which food is most popular in the cafeteria, then your system would be the cafeteria and the lunch, like the kitchen and all of that area, because that's where you would be gathering your data from. So it's very important to define your system so that you are only gathering data that's relevant to your experiment. Next up, formulating a hypothesis. After we've made our observations and we've decided what our system is, now we have enough information to make a hypothesis. Okay? Because in order to make our best guess of what is going to happen, what is the answer to our question, we have to have seen enough and known enough about our system to even make an educated guess. So, we take our data, we analyze it, and based on our data, we make generalizations. A hypothesis is a generalization about data that is testable. Okay? So, you might survey students to find out which lunch they believe is most possible. That's you gathering some data. And then you're going to generalize and say, I think that the pizza is the most popular dish. Okay? That would be your hypothesis, and that's testable because then you can go and get data about how many people eat specific lunches and really determine which lunch is the most popular. So you have a generalization, and that generalization is testable. Perfect, thank you. These are the basis for making predictions about future data, and they should be specific, and they should be supported by data you have already gathered. So you don't want your hypothesis to be wild and out there, okay? You wouldn't want your hypothesis to be a lunch that we don't even offer here at school will be the most popular, okay? And you need to be able to test it and gather data about it, and it needs to be specific. I will provide ingredients. Please come make the cookies.
Like just guessing it or what?
Oh, is there something else you need?
No. The measurements, the instructions.
Yeah. There is something else you need in order to successfully make the cookies. It is not a trick question. You probably need a recipe, right?
Right.
Yeah, okay. So I will also provide the recipe for you to make the cookies. Okay. I promise there's a point behind the cookies. Okay, we'll get to it here shortly. We're going to talk about the testing stage, because after you have your hypothesis, what comes next is the testing stage. So you've made your prediction, and then you're going to design your test. You're going to identify any variables, which ones you're going to control and keep the same throughout, which variables you're going to change, and then what things are you going to measure about this. If the testing doesn't support the hypothesis, it must be discarded or modified. So when you get to the end of your testing, okay, if your hypothesis is not supported, then you need to either modify your hypothesis or discard it, okay, and come up with a whole new one. Okay. The data that you record must be recorded in a way that allows for replication and repetition, okay? So just like you required a recipe with specific detailed instructions and measurements, other scientists are going to want to replicate your experiment, and they are going to need even more precision than a recipe, okay? For a recipe, we often have ingredient names and amounts, cook times, chill times, a list of tools that you might use, okay? But no one is going to tell you exactly what size of wooden spoon to use in your experiment. They're probably not, in your cookie making. They're probably not going to tell you what brand of peanut butter you need to buy, but that information would be important if you were doing a science experiment. You would want to report the brand of peanut butter you used so that people could duplicate your experiment exactly. Your measurements need to be precise and accurate and written down, how much you used of things, how long you let things sit, because that stuff, as little as it sounds, can be the difference between someone being able to accurately replicate your experiment and not. So when we do science, we record everything. And to go back to the candle from the beginning, the most useful information for us in terms of a science experiment is quantitative data, numerical data, okay? It is nice to know, okay, that the peanut butter tastes good and the cookies taste good and that people liked it. But more important would be numerical data. How long did you bake them for? How much peanut butter did you use? Okay, that is going to give people actionable material to work with. So, very important. Then we move on to theorizing. Okay. When you have a hypothesis that is supported by data, we don't just stop there and never test it again. Okay? We test it over and over and over in new and different ways. And if that hypothesis keeps turning back up as accurate, then it forms the basis for a theory about how the world works. Theories tend to be a little broader than a hypothesis. They might not be as specific and detailed, but they have been supported frequently. And a theory might inspire a model or an explanation of how a phenomenon occurs. The one that I think students might be most familiar with is the theory of plate tectonics. Okay? The theory of plate tectonics explains how the surface of the Earth is broken up into plates and how currents in the mantle cause plates to move around, new crust to form, old crust to be destroyed or deformed. So that theory is not like proven scientific fact. It's just the theory that has been proved, has had supporting data to go with it the most and the longest. Okay? If new data comes to light that shows that that theory is inaccurate, we will develop a new theory for how the Earth's plates move. But for right now, all the tests we run keep turning back up that one as accurate. And the last step we're going to do is we're going to publish our results. This is important for that repeatable step. Okay, if we never publish our results, then no other people can test to see if we were accurate. Because when we design experiments, sometimes we design them poorly, sometimes we don't conduct them very carefully, sometimes we have internalized biases. So it's important that other people can replicate our experiments, and if they come up with the same results as us, then it lends more credence to our experiment, because it's saying, this experiment was not flawed. Multiple people have now run this experiment and come up with the same results. All right. That's it. That is the whole scientific method.